Okay. Good afternoon. Can you hear me?
Yes, sir.
Good afternoon, sir.
Oh, yeah, good afternoon. Okay. So previous class, in the yesterday's class, we went through the hardware components of embedded system, and then we went through the software components of embedded system. Four major software components of embedded system. One is the initialization code or the bootloader code, and then the device drivers, operating systems, okay, and then the applications. So we focused more on the initialization code and then the operating system. Again, you understood how many different operating systems the ARM processor supports. It supports around 50 operating systems, and then you understood the broad categories of the operating systems that are supported by the ARM processors. So they're divided into something called as real-time operating system and POS. So that is platform operating system. Platform operating systems are the one which we use in the personal computers, and real-time operating systems are the one which we use in the embedded devices. And again, two classification of real-time embedded systems, real-time operating system we understood, hard real-time operating system and soft real-time operating system, along with the examples. So now we'll discuss chapter 2, so which is mainly on the ARM core, okay, and we are going to understand the internals of the ARM core right now. Now what you're seeing here is the data flow model for the ARM processor or microcontroller. Now as I already explained to you people in the pipelining, so when I was explaining in the earlier classes the concept of pipelining, I told the first stage within the pipeline is the instruction fetch stage, and that is what here it is not written, but this is what is the instruction fetch stages. So you fetch the instruction. So here we can assume the pointer where I'm moving, so there is an instruction fetch stage. It fetches the instruction, and once the instruction is fetched, so it is decoded. So we have the instruction decoder, which is decoding the instruction and identifying the opcode of the instruction. So opcode, all those things I've already told you. And then so we have a sign extended hardware here. So what it is going to do, it's going to convert the operands. So, and this instruction decoder is also responsible for reading the source operands. So what the sign extended hardware is going to do is, so if the operand is only 8-bit or 16-bit, then it gets its sign extended to 32-bit. So because the capacity of all the registers in ARM7 design is 32 bits, so even if you're giving the data which is of only 8-bit or 16-bit, it gets sign extended to 32-bit. Okay, so 32-bit data. Say for example, I'm giving the input as the number 16, okay, which is only a byte of data. It gets sign extended to what? 32-bit. So what is the meaning? So the value is 16 itself still, but you have zeros added to the left side of it, and makes the number as 32-bit. Number is 32-bit, but still the value of it is how much? 16 itself. Okay, so that is what is sign extended hardware. So OP people understood what I mean to say?
Yes, sir.
Yes, sir. Say you're giving an 8-bit data. So say for example, I write the digit 5. Okay. So digit 5. So or 05. It is an 8-bit data. Now when I'm giving the 05, now the register capacity is 32-bit. Now how this 05 is going to store inside the register? It is not only a byte. It is a 32-bit. So the length of the word is 32-bit, but the value is still 5. That is what is sign extended. Okay, and then we have the register file here. So in the earlier classes when we were discussing the ARM design philosophy, we understood that the ARM design philosophy has rejected the concept of register window. So that is what is made used by the, because for register window occupies the larger chip area. So now what it makes use of, instead of the register windows, it makes use of something called as a register file. And you have all registers here from R0 to R15. Okay, so this is something like a register file or a register pool where all the registers are available. Next, you take the data, sign extend the data, and write the data into the register. So before writing the data to the register, they got to be sign extended. So even if you're giving a data which is only 8-bit or 16-bit, it gets sign extended to 32-bit and then stored into the register file. Okay. First, so let me brief again. So fetch the instruction or the data. So it is decoded. Once it is decoded, the opcode is identified. So we go for, if the data is lesser than the 32-bit, we go for sign extending it and make it as 32-bit, and then we store them into the registers. Okay, here inside the register file, you have access to all the register R0 to R15. Okay, and then so here is the ALU. So this is the main execution engine. Okay, so you take the data. So this is the bus A, and this is the bus B. And as I already explained to you people, one of the ALU input is connected with the barrel shifter. Okay, so the bus A. So the data RN is given to the bus A and it comes to the ALU. And the other data, if you want to perform more complex operation, so it can be, that is another data is RM. So which can be given to the bus B, and the bus B is connected to the barrel shifter, and inside this you can go for performing the shifting operation, and that result what you get can be given as input to the ALU. Okay, and this ALU performs the arithmetic and logic unit. And now there is another thing, the special hardware called as MAC, multiplier and accumulator, and this is most widely used for in digital signal processing. And again, this is also used for multiplication operation. See, multiplication operation here will not happen inside the ALU. Instead, it happens within the MAC. See, when you're multiplying two numbers, it is not possible for you to make use of the barrel shifter, because so there is no barrel shifter connected to the MAC. And all these things you'll understand when we start writing the program. Say, for example, when I'm writing the add instruction or subtract instruction, okay, or the logical AND or, it is possible for you to perform the shifting operation on one of the operand, but it is not possible when you're multiplying. When you're multiplying, so the shifting barrel shifter is not available. You can see here, so the barrel shifter is not connected. Okay, you take the input, first input, second input, then perform the multiplication operation, store the result back. This is the accumulated multiplication or result, and it can involve in repeatedly doing the multiplication operation. Okay, so hope people understood what I mean to say here. Hello. So multiplication, so just remember this. So this architecture you should always keep in mind. So MAC, there is no barrel shifter connected. Barrel shifter is connected only to the ALU. So when you're performing addition, subtraction, multiplication will not happen here. Multiplication will happen here using this device, this hardware. Now, when you're performing the multiplication operation, so you cannot use the shifting operation on one of the inputs. Say, for example, I want to shift to B and then multiply, not possible. Okay, so it is possible only with the addition, subtraction, and any logical instructions. Okay, next. So once the ALU or MAC finishes their execution, so you get the result, and that result is written to the destination register RD. So this is what the result. So once the result is written here to this path, this bus, from there it goes back and sits inside the destination register. Now RD is the general convention which we are using. So for the first source register is represented as RN, the second source register is represented as RM, and the result, which is computed in ALU or in the MAC, once it is written to the bus, okay, it is a common data bus which carries the result from both ALU and also the MAC. You don't have a separate bus here. Separate bus for carrying the result from ALU back to the register file, and separate data path is not there for carrying the data or the result written by the MAC back to the register file. It is the common data path or the result path which is available for both ALU and MAC. So they write here, and it goes and sits inside the destination register, and that is represented as RD. Okay, next. So this ALU, so also involved in computing the addresses, memory addresses. Okay, so there is something called as logical address and physical address. I don't know whether you people have studied this in CO or not. So the addresses which are generated by the CPU, we call them as logical addresses, and and to this logical addresses, okay, when you add the base address, you get the physical address. Okay, OP people know about the logical and the physical addresses.
No, sir.
Yes, you don't know.
No, sir.
No, sir.
Okay, yeah. Let me show you. Say I'm writing here. Say this is the CPU. CPU. Okay, and here I have the memory. So where all my instructions are stored. Okay, so let us assume the starting address of this instruction where it is, this instruction is present at address 1000. Now let us take the size of each instruction as how much? 4 bytes. So because we are discussing ARM7, so and the next address of this instruction will be 1004, the second one. And then this instruction, it is at address 1008. It goes something like this. And this instruction is at address 1012. Right? It goes something. And we have something called as base register. BR, let me write base register. Okay. And what this base register will be holding? This base register will be holding the starting address of my program. Where is my program starting within the memory? It is starting from the address 1000. Okay, 1000. So base register is holding the address 1000. Now this CPU, what it generates the logic. Say when it wants to access the first instruction. So this instruction. Okay. So it's just going to generate the logical address. So because CPU knows size of each instruction as 4 bytes. So when it wants to access this first instruction, it generates the logical address 0. And this 0 is added with the base register, content of the base register. So 0 plus 1000 is how much? Hello? 1000. So that is what is the L is logical address plus BR. BR gives you physical address. So the actual address where the instruction is present inside the memory. But what CPU generates is the logical address. So logical address 0 plus 1000. It is 1000. So now, so this is the physical address and this is the instruction that is accessed. When CPU wants to access the next instruction, say this 1004, it generates the logical address 4. So 4 plus 1000, how much it is? 1004. This is the physical address. OP people are following.
Yes.
Hello. Hello.
Yes.
Yes, sir. Yes, sir.
Yeah. See, the main advantage of this is, say for example, now my program within the memory it is located. It is starting from the address 1000. So I need to relocate my program. Okay. So say the address. So when I'm relocating, say the address is not 1000. It is simply 2000. Okay. What happens? So now this all my addresses gets changed to 2000 and the BR is also updated to 2000. Okay. So earlier it was at 1000, now it is 2000. So it is starting. My program is relocated within the program. Now my CPU is least bothered about this. Okay, it is relocated, and once the program is relocated, BR will be updated with the starting address of my program. Earlier it was 2000, now it is 2000. Now CPU is never bothers about these things. What it will do, it will simply go for generating. When it wants to access the first instruction, it generates 0. When it wants to access the second instruction, it generates the logical address 4, and that gets added with this 4. Now see, for example, now the CPU wants to access the second instruction of my program. So it doesn't know where it is. What it does is it generates the logical address 4, and this 4 gets added with the base register. And now it is sure that the instruction what the CPU is looking for is present at address 2004 inside the memory. Hope you people are following.
Yes, sir.
Hello. Yeah. Now to generate these physical addresses, what is the operation you're doing here? What is the operation?
Addition.
Adding logical address with the base register content. Now who will do this addition? This ALU, right? Okay. So ALU is also responsible for generating the addresses. Okay. So the physical addresses it will generate, and those physical addresses are stored into the address register. Okay. So it performs addition, subtraction, all logical operation. But in addition to this, so this ALU is also responsible for generating the physical addresses by adding the logical address with the content of the base register. That adds and writes the physical address to the address register. And within once the physical address is written to this address register, it can be auto incremented or auto decremented. So this is what we understood in the previous class when I was mentioning the additional features that are supported by the ARM. So the address register is auto incremented and auto decremented. Okay, so this is what it is. Here only incrementer is shown. So similarly, you can also write it as incrementer / decrementer. Okay, once the address is generated, so based on that physical address, you can go for accessing the next memory location by auto incrementing and auto decrementing the value which is there inside the address register. So this is what is the complete data flow model of the ARM core. Hope you people understood here.
Yes, sir.
Yes, sir.
Yeah. So and R15 is the program counter. We'll understand all these things details now. So R5 to R15 registers, everything you will be understanding in detail. So I guess all of you understood this. So what does incrementer or decrementer does? It takes the physical address which is written by the ALU to this address register, and it will go for incrementing or decrementing based on the situation. Okay. So if you're starting from the lower address and if you want to proceed towards the right side, then it increments. If you're starting from the higher address and if you want to proceed in the reverse direction, and then it start decrementing automatically. Okay. So this is what the ARM code. Okay. So you fetch the instruction, it is decoded, and it will check whether the size of the operand is less than 32-bit. If it is less than 32-bit, it gets sign extended to 32-bit, and then the data is stored inside the registers, any one of the register, because all of them are general purpose register, R0 to R15 you can use. Once they are stored, so depending on the operation, okay. So if the decoded instruction is an arithmetic instruction like addition or subtraction or any logical instruction, it takes this path. It takes this path. So the first input comes here, the second input goes here, and if you want to perform shifting, you can perform. If you're not performing any shifting, the same input is given to the ALU. If it is a multiplication operation, then it goes here to the MAC. And from this architecture, it is clearly understood that so when you're performing the multiplication operation, it is not possible for you to shift the other input. Okay, so this. Okay, now we'll come here. So most of the things I've explained here itself, but anyhow, we'll go through this. So first thing is instruction fetch. I said that is not written here, but it is understood. Okay. So the data or instruction enters into this ARM core from the instruction fetch stage. Okay. Instruction fetch. What it does, fetches the instruction from the memory. So where is it? Where it is happening? At this place. And next, instruction decoder. What it do? It decodes the instruction and also identifies the opcode of the instruction. And next, sign extended hardware. What it will do? It will convert a signed 8-bit and 16-bit numbers to 32-bit values. Okay. So this I can demonstrate also. So because we have executed the programs, and I don't know whether you people remember. So we did the addition program and subtraction program. For doing the addition program, we moved the number 11. Okay. Move R0, #11 we wrote. Now and in the register it was B. Okay, instead of 11 it was B, 00. How many zeros? 7 zeros and a B. So this 11, which is an 8-bit, got converted, sign extended to how many bit? 32-bit. So it occupied the entire 32-bit register, and towards the left side, what was there? All zeros, and then A. So that is what is sign extending. So sign extend hardware converts a signed 8-bit and signed 16-bit numbers to 32-bit values. So as they are read from the memory and placed inside the register. Inside the register, you cannot place an 8-bit, or you cannot place a 16-bit number. So what you can place is only the 32-bit values. So when you're reading something from the memory, if it is a bit, if it is a byte or 2 bytes, so then it got to be sign extended to 4 bytes or 32-bit values. Next is ALU, what it performs, arithmetic and logic unit. And then we have MAC, multiply and accumulate unit, for performing the multiplication operation. For all arithmetic operation, addition, subtraction, and logical operation, we make use of these things. And takes the register value Rn, Rm from the buses A and B and computes the result. So this is the register Rn and this is the register Rm. So when I say Rn, it is the first source register. Rm is the second source register. So content of these two registers are read and fed into the corresponding buses, bus A and bus B. And then you perform either the ALU operation or the MAC operation. Okay. Next. So data pre-processing, data processing instruction, what they do? So any data processing instruction, okay, they write the data or the result to the destination register. So it goes to the destination register, which is present again inside the register file. So if it is a load and store instruction, so they do what? They compute the effective address or the physical address. Okay, they generate an address to be held in the register. Which instruction? Load and store. You know load. What is load is? Reading from the memory and loading it into the register. What is store? From the register to the memory. Now both load and store, they require the computation of physical address. Okay, and for that purpose you require the ALU. So now when it computes the address, it need not be fed back to the register. Instead, it should be written to the address register. Okay, and the address which is here can be auto incremented or auto decremented. Okay. I guess, and that is the same thing which is written over incrementer or decrementer, incrementer or decrementer, and the same thing happens. Next. So I guess you people understood till here.
Yes, sir.
Yeah, excuse me. Hello, madam. Amel Madi, madam. Class alli dinna. Madam, ಈಗ ನನ್ನ ಕ್ಲಾಸ್ ಅಲ್ಲಿ ಕಳ್ಸಕ್ ಆಯ್ತದ? So next is registers. Okay. So as already discussed, registers here are general purpose registers. So they can hold both data or address. Now how registers are identified? So they are identified with the letter R. So they prefixed with the letter R to the register number. So for example, something like this. So register 4 is labeled as something like this, R4. And even we have already used them in the program. We wrote R1, R2, R3, something like this. Okay. So the register R0 is labeled something like this, R0, R1, R2, R3, R4, R5, something like this. So these are all the registers. You can see here R0 to R15. So among this R0 to R15, so the last three have some special usage. Okay. So this R13 acts as the stack pointer. That means it points to the top of the stack. And LR is the link register, which is used to hold the return address when the subroutines are called. So whenever a function is called, so the return address should be saved onto the stack. We used to store the return address onto the stack, but here in ARM, the return address is not saved onto the stack. Instead, whenever the subroutine is called, the return address is saved onto the link register. Say, for example, I've written a main program here. Say this is main. Okay, I'm writing C program. I'm just showing you some C program just to make you understand. Say from here, I'm calling a subroutine with the name sub. And after this, there is an instruction here, and say the definition of the sub is here. Okay, when I'm calling this function from here, so before the control goes here, address of this statement. So address of this statement will be returned to the LR register. That is a link register. Okay, which stores the return address when a subroutine is called. And R15, as you already know, it acts as the program counter. Okay, so there are 16 general purpose registers. Okay, and then in addition to this, there are two more registers. Okay, one is Cpsr, another one is program status register. So one is current program status register and program status register. So these are the registers. So people understood and how the registers are named?
Yes, sir.
Okay.
Sir.
So among this R0 to R15, these are special registers. Cpsr and PSR are the special registers, and these are the general purpose registers. Among these general purpose registers, the last three have some special meaning or the special usage. So R13 acts as the stack pointer and R14 acts as the link register. I guess all of you understood what is a link register is. It's going to store the return addresses whenever the functions or the subroutines are called. And then R15 acts as the program counter. Now, so processor can operate in 7 different modes. So don't confuse. So earlier in my previous class, I was telling, so the ARM processor or microcontroller can operate in 3 different states. States is different and modes is different. How many modes the ARM processor can operate? 7 modes. If I ask you how many states, in how many states the ARM processor can operate, what is your answer?
3.
3. It can operate in 3 states. 3 states. Don't confuse. So usually you'll confuse with this. It can operate in 3 states and in how many modes? 7 modes. Okay. So the ARM processor can operate in 7 different modes. Now, what are those 7 different modes? You'll understand. Okay. And all registers shown are of capacity 32-bit. Okay. And there are up to 18 active registers. So how many active registers? 18. What are they? So this R0 to R15, how many? 16 registers total, because starting from 0 to 15, 16. And there's two special registers. Okay, one is CPSR and PSR. So current program status register and program status register. 16 plus 2 is equal to 18. There are 18 active, okay, registers. Okay, among this 18 active register, 16 are data registers or else address register. You can store either data or address because they're general purpose, and 2 processor status register. Okay, so 2 are processor status register. What are they? That is CPSR and PSR are the processor status register. Okay, 16. Now 18 active registers. Now the visible registers to the programmer are R0 to R15. That means you can go for using R0 to R15 registers for as a programmer. You can use them. Okay. Now, and again, so in this visible registers, so R0 to R15, 3 registers are assigned to a particular task or special function. Now, what are those registers? R13, R14, and R15. So we have R13 acting as SP, stack pointer, and R14 acting as LR, link register, and R15 acting as PC. These 3 registers have the special meaning, and the same thing is mentioned here also. So R13, register R13 is acting as a stack pointer, so which is going to point to the head of the stack, and R14 is called as a link register, which is going to store the return address whenever a subroutine is called, and R15 is a program counter which holds the address of the next instruction to be fetched by the processor. So is that clear till here?
Yes, sir.
Yeah. So even though we say R0 to R15 are general purpose registers and they are programmer visible register, so we always prefer using R0 to R12. So you can use whatever way you want, but we don't prefer using R13, R14 and R15 since they have special function. So for some cases and some reasons, say for example, if you're using program counter, so then your processor will not be knowing. So it's not like you cannot use. You can use PC also. So then what will happen? Your program, sorry, the processor will not be knowing. That means you're overwriting the content of the PC, and your program execution will be what something like episode. It doesn't know what it is executing. So it goes here and there and jumps here and there. So you got to be careful. So it is not restricting you people not to use R13, R14 and R15. So you are free to use, but when you're using, you got to use them very carefully. That means, say I have used R0 to R12, all my registers are full. So now I need to use one more register or two more registers or three more registers. Then what you got to do is you got to appropriately take the backup of R13, R14, R15, take the backup, use them. After using, so then again put these registers with the original content of original content which was there in these registers before. Use them for your own purpose. Hope people understood what I mean to say.
Yes, sir.
Yeah, so it's not like it will not restrict you from using this R13, R14 and R15 for your own purpose for storing something. You're free to use, but before using these registers, you got to take the current backup, the current values in these registers. You have to take the backup and then use this register and then restore the values back to R13, R14 and R15. Okay. So then your program works fine. So if you're not doing this properly, if you're not taking the backup of R13, 14, 15 before using them, so then your program will definitely behave in an abnormal way, and you won't get the expected results. Okay, so let us move on to the next thing. Okay. So depending on the context, this is what I explained here to you people. Depending on the context, R13 and R14 can also be used as a general purpose register. Not necessarily R13, R14. R15 can also be used, but so it is not recommended to do so, because all the time it's not like you are cautious and you'll be taking the backup and you'll be restoring them after doing the processing. So sometimes here and there we go wrong. So and we say dangerous to use R13, R14 and R15. So as much as possible we try to avoid this R13, 14 and 15 for our own purpose. So we'll let them go with their special functions instead of disturbing those registers. Okay, got the point?
Yes, sir.
Okay, only when it is inevitable. Say I have used all the 13 register R0 to R12. I don't have any other option. Now I need to try with R13 or R14 or R15. Yes, you can. But before doing so, so you got to be cautiously taking the backup of these registers, do the processing, and don't forget to restore. So this is what you got to do. If you're doing it very cautiously, then good. So otherwise, we say it is dangerous to do. Okay. Okay. And in addition to the 16 data registers, so what we mentioned R0 to R15, there are two program status registers, or you can also call them as processor status registers. They are current program status registers and program status registers. Okay. You can short form also call it as program status register or saved program status register, SPSR. So I prefer calling it as PSR, program status register. Okay, and this I call it as current program status register. So this is only current program status register, and this is program status register. Or else if you would like to call it as SPSR, no problem. You can call it as SPSR. So these are the status registers. Now, so time to understand. You understood? Okay, these are the general purpose registers from here to here. All of them are general purpose register, but they have, these three have some special meaning. Now, what are this program status register or program processor status register? There are two. One is CPSR and SPSR. We'll try to understand this current program status register. Okay, so it is again the capacity 32-bit. You can see here 0th bit till 31st bit, and what it has flags. Okay, and again this current program status register, which is a 32-bit register, is divided into 4 parts. So what you're seeing it as flags. It is divided into flags and something called as status, something called as extension, and something called as control. Now, what is the capacity of flags? 8 bits. What is status? 8 bit. What is extension? 8 bit. What is control? 8 bit. 8 plus 8 plus 8 plus 8 is 32 bit. That is what you're seeing here. Okay. Now, okay, sir, fine. So this you have written something mode and T and here F and here I and here N, Z, C, V, and why this is blocked. So this is what is reserved for future extension. Okay. Now I mentioned, I don't know whether you people remember or not, everything is connected component here. So in the first or the second class, I said when you're designing an embedded system, you got to design in such a way that so it should be easy for you to do the future extension or the future expansion. Okay, and these are the bits which are reserved for future extension. Okay, and few bits I'll try to highlight here also. Okay, so it was reserved for future extension, but few are already extended. Okay, I'll show them now. So this is let me start from here. So the mode, right? This is the mode, processor mode. Can you just answer me in how many modes the processor, ARM processor operates? What are the number? I just now told you people. 7 modes. 7 modes. As of now, it operates in 7 modes. And how many states? 3 states. Okay, and these are the bits 0 to 4 reserved for indicating the mode of the processor. So you might ask me a question, sir, you said as of now the ARM processor operates in 7 modes. To specify the 7 modes, why do we need 5 bits? 0 to 4 is 5 bits. 5 bits are reserved. Using 5 bits, so totally how many modes you can specify? 16 modes you can specify. Okay, so why 16? So 5 bits are reserved just to specify 7 modes. For specifying 7 modes, 7 different modes of operation of the microprocessor or the microcontroller, you require only 3 bits. 0 to 2 is enough, but 0 to 4 is fixed. Again, this is for future extension. So as of now, it is operating in 7 different modes. So, but still, this processor in future can be made to operate in 16 different modes. OP people are following? Hello?
Yes, sir.
Yeah. So don't confuse, sir, 7 modes, and but the number of bits reserved to indicate the mode is 5. So as of now, this ARM7 microcontroller, in how many modes it is operating? 7 different modes, but still it can be made to operate in 16 different modes. Okay, so till 16 modes it can make it to operate because the number of bits reserved are 0 to 4. Say when it is 0 0, all 5 bits are 0 0 0. Mode 1. What is that mode 1? We'll see later. And when it is 0 0 0 0 0 1, mode 2. When it is all ones, 1 1 1 1 1, 4 1, sorry, how many ones? Sorry, 5 bits, right? So 5 bits means how many modes it can operate? If it is 4 ones, 16 modes. So now 32 modes it can operate. You can make this ARM controller operate up to 32 modes, up to 32 different modes. OP people are able to understand?
Yes, sir.
1 1 1 1 1. So this is how much? What is the value of this? What is the decimal equivalent of this?
32.
32.
Sorry, 31. 31.
Yeah, 0 to 31. 0 0 to 31 it is. Nothing but 32 different modes. OP people are able to understand?
Yes, sir.
So this binary equivalent is 31. But it starts from what is the minimum value? 0 0 0 0 0 0 to 111. So how many modes? 32 different modes. You can make it to operate in 32 different modes. So that is with what for future extension. Okay, so now as of now it is operating in 7 different modes, but still this can be made to operate at 32 different modes. Okay, so the mode To some extent you understood. Right now you don't know what are those different 7 modes. Okay, we'll understand them later. Next, let us move on to the next bit, 5th bit. What is it? You can see here. Can you see this? What is it?
Thumb state.
Thumb state. So if you want to make your ARM processor operate in the thumb state, then this 5th bit in current program status register in Cpsr register should be made as 1. If you make this bit as 1, your ARM processor or ARM microcontroller operates in what state? Thumb state. So don't say thumb mode, thumb state. Understood, right?
Yes, sir.
Okay. Next. So this is clear. So and you can ask, sir, okay, this is fine. Thumb state. Where is ARM state? In the ARM state, it uses 32-bit instructions, right? Now, where is the ARM state? I'll tell you. Okay. And where is there? What is the other state?
Jazzle state.
Jazzle state, or simply you can also call it as J state. Now, see that was here in the status. This is 28th bit, right? 28th, and that is 24th bit. So this is so now it has already extended. Okay, so 24th bit, but it is not shown here. The 24th bit is the J bit, Zazzle bit. Okay, so now if this Zazzle bit is 0 and the thumb bit is 1, your microcontroller operates in what state? Thumb state. Say I want to make the microcontroller operate in the Zazzle state. I need to make this 24th bit as 1 and this 5th bit as 0. Now you have your ARM microcontroller operating in the Zazzle state. No, I don't want to operate it in the Zazzle state. I don't want to operate it in the thumb state. I want to make it operate in the ARM state. Then make this as 0 and make this also as 0. When T bit is also 0 and J bit is also 0, J bit in the sense that 24th bit is 0 and 5th bit is 0. So it operates in the ARM state, and this is the default state. OP people are able to understand.
Yes, sir.
Yeah, J is 0, T is 0, it is ARM state. T is 1, J is 0, it is thumb state. J is 1 and T is 0, Zazzle state. So you cannot have J and T both 1. Okay, so if you make both of them 1, you're making the ARM controller to operate in both the Zazzle state, also in the thumb state. How can it be possible? It is something an invalid state. Okay, next. We'll come to this 6th bit, F. So I said interrupts. Okay, interrupts. And 2 types of interrupt controllers also you understood. Can you just tell me what are those 2 types of interrupt controllers? Yesterday we discussed, I guess, yesterday or day before yesterday, I guess. What are those 2 types of interrupt controllers?
Hardware
SIC,
control and
yeah, SIC and VIC. Standard interrupt controller and vector interrupt controller. Able to recall?
yes, sir. Yes, sir.
I don't know, you might have forgotten. So 2 controllers, standard vector, standard interrupt controller and vector interrupt controller. So only thing is how vector interrupt controller is different from the standard interrupt controller. So in vector interrupt controller, it is possible for you to prioritize the interrupts. So this is the additional feature which we have in VIC. So apart from that, the remaining things are all same. Okay. So even you can go for masking the interrupts using SIC, and using VIC also it is possible for you to mask the interrupt. And now what is here F and I? So there is something called as in interrupts also fast interrupt and slow interrupt. Okay, so this F is fast interrupt and this I is normal interrupt, or you can also call it a slow interrupt. Okay, say I want to disable, ignore, I want to make my processor ignore or mask the slow interrupt. Okay, make it as 1. Okay, people are following?
sir.
It's a bit. 7th bit it is. Either it can be 0 or 1. So if I want to make my processor or microcontroller ignore all the slow interrupts, okay, so then this I bit, 7th bit must be made. If this 7th bit is set, your processor or microcontroller is going to just ignore all the slow interrupts. Okay, I want to make my microprocessor ignore the fast interrupts also. Make it as 1. Set this fast interrupt flag. Make it as 1. Now even the process will go for ignoring the fast interrupts also. Okay. Now I want to make my processor ignore only the slow interrupts. Okay, but not the fast interrupts. Make this bit as 0. That is what is interrupt mask. OP people are able to understand? Yes or no?
Yes, sir. Yes, sir.
Okay. 1. To make the microprocessor or microcontroller ignore the interrupts, so the corresponding interrupt of either the slow interrupt or the fast interrupt, so the corresponding interrupt bit here, it should be set or reset. It should be set. If it is set, it ignores. Okay, so I don't want the microprocessor to ignore either the fast interrupt or the slow interrupt. Then make this 7th bit and 6th bit as 0 0. That's all. Okay, that means your processor is not ignoring anything. So even if the slow interrupt comes, yes, it will pay the attention towards. Even if the fast interrupt comes, it will pay the attention towards it. So I guess you understood from 0th bit till 7th bit. Yes or no?
Yes, sir.
So these are called as control bits. Control bits. Okay, this is 8 bits. So mode, then the thumb state, fast interrupt, slow interrupt. And these are all reserved for the future extension. Okay, but in that we have already explored the 24th bit, and it is the J bit. Okay, the Zazzle bit. Next, coming to here, flags. Okay, these are called as flags. So this is negative flag. So whenever you're performing some operation, some kind of operation, when ALU is performing some kind of arithmetic or logical operation, and if the result of that operation is a negative number, okay, so then this bit will be set. So negative bit will be set to 1. Whenever, so I want to know whether the result of the operation that is performed by the ALU is positive or negative. How do I know? I just go and check this n bit inside the Cpsr. If this n bit is 1, set to 1, what does it mean? The result of the operation that is performed by the ALU, the result of the most recent operation that is performed by the ALU is a negative result. Hope people understood?
Yes, sir.
Okay. And how do negative numbers are indicated here? The leading, the 31st bit. So the capacity is 32 bits, right? The 31st bit, if that bit is 1, it is a negative number. If that bit is 0, it's a positive number. Which bit? 31st bit. The MSB bit. So you're starting from 0th bit. Okay. So you have some bits here. So this is the sign bit. Always the most significant bit. Okay. Or the 31st bit is the sign bit. If this is 0, it's a positive number. If this is 1, it's a negative number. And whenever you find whenever the ALU performs some operation and the result is something like this, the bit value in the 31st bit position, if it is 1, so it's a negative number, and this negative bit flag is set. Is that clear?
Yes, sir.
Okay. Next, 0 flag. Z sign for 0 flag. If the result, if the most recent operation that is performed by the ALU results in a value 0, getting? So either it could be an addition operation or a logical operation or a subtract operation. When you do this, if the result is 0, so then you have the 0 flag set. Hope people are understanding.
Yes, sir.
If the result of the most recent operation that is performed by the ALU is a negative number, then this bit is set. If the result of the most recent operation that is performed by the ALU is a zero value, is zero result, then this flag is set. So it becomes 1. Now just by examining the zero flag, and when I examine the zero flag, if the zero flag bit value is 1, so I'll know that. So the operation performed, the most recent operation performed by the ALU resulted in a value 0. Okay. And similarly, next carry flag. Say when I'm performing the arithmetic operations or the logical operation, if that operation resulted in a carry, so then the carry flag is set. If the most recent operation which is being performed by the ALU, if it is not resulting in a carry, if there is no carry generated, so then this carry flag will be still 0. Okay. Next, overflow flag. V stands for overflow. Okay, it is not named as O. V stands for overflow. Say for example, I multiply two 16-bit numbers. Two 16-bit numbers. What is the maximum? No. This 16 is not a number. 16-bit number. Okay. When I multiply two 16-bit number, the result what you can get is 32-bit. Correct, right? 32-bit product. Yes or no?
Yes, sir.
Okay. Say when you multiply two 2-bit numbers. When you multiply two 2-bit numbers, what is the maximum result you can get? Say
4 bits.
Yeah, say I want to represent 2. Okay, it's a 2-bit number. Only 2 bits are sufficient. I'll write it as 1 0. So another 2. I'll write it as 1 0. Correct, right? Yes or no?
Yes, sir.
2 is a 2-bit number. Now I multiply this 2. 2 into 2. What is the result? 4. Correct, right? And this
Yes.
4 is a 4-bit number. Say I cannot represent this 4 using 2 bits. So I got to write it as 1 0 0 0. Okay, but 3 bits you cannot write. So always it should be in integer power of what? 2. Yes or no?
Yes, sir.
Always it should be in integer power of 2. So this 2 is okay because this is 2 raised to 1. And this, can I write it as integer power of 2? Not possible. I got to add one more 0 here. Now this is 4-bit. So 2 raised to 2. So this can be expressed. Now the product what I'm getting is a 4-bit number. So similarly, when you multiply two 16-bit number, the maximum product what you can get is 32-bit. And similarly, when I multiply two 32-bit numbers, the maximum result what I get is what? 64-bit. Now the register capacity is only 32-bit. Is it leading to an overflow? Yes or no?
Yes.
Yes, the product what I get, 64-bit product, I cannot accommodate in a register. Now it is a overflow, then you have the overflow flag set. Okay, now I go and check whether there is a overflow. Okay, is the register capacity not sufficient to hold the result that is produced by the ALU? Then what I do, I examine this. Okay, overflow flag is set to 1. So now I cannot put the entire result in one register. So I may have to use several such registers. Okay, so this is negative flag, zero flag, carry flag, overflow flag, Zazzle flag, interrupt, slow interrupt flag, fast interrupt flag, thumb state flag, and this is mode. So I guess you people understood. So these are our focus will be on these things, and even we don't use this Zazzle state also. So NZCV and then IFT and then mode, and the rest all is not required for us. And this J I showed you for your curiosity. That's all. Is that clear?
Yes, sir.
Yes, sir.
And the bit position for J is 24 itself. That is fixed. I know for sure it is the 24th bit. Okay, next. Now, see, if you want to make your processor operate in these 7 different modes, or if you want to make your process operator in the thumb state, okay, or in the Zazzle state, or in the ARM state, so you got to program. Program using what? The Cpsr. You need to set the desired value, required value to this Cpsr. Okay, so I want to make my CPU or processor ignore the slow interrupts. So you got to write the program in such a way that you push the value 1 to the 7th bit of CSPR. That is what is meaning of programming. Hope you people understood. Yes or no?
Yes, sir.
Okay. Next. Okay. So a whole lot of things I've explained here itself, and this is what the explanation for the same thing. So ARM core uses the Cpsr to monitor and control the internal operations. Okay, and Cpsr is a 32-bit dedicated register which resides inside the register file. And where do you find the Cpsr again? So Cpsr is also found inside this register file. Here I've shown R0 to R15, but Cpsr and the SPSR are also present here. Okay. And the shaded parts are reserved for future expansion. Okay, but the one bit we have already explored, that is the J bit. And next, CPSR, again, it is divided into 4 fields. One is the flags, status, extension, and control. So flags, status, extension, and control. And you have understood all of that. And the rest all are reserved for the future use. Next. Now we are focusing on this control field. I've already explained. Okay, so we are focusing on this control field, this part of the CPSR register. So the control field contains this processor mode, state, and interrupt mask bits. 3 things. It contains the processor mode, state, thumb state, and then interrupt mask bits. So slow interrupt mask bit and fast interrupt mask bit. Hope people are able to understand.
Yes, sir.
Okay. And then the flag field contains the conditional flags. Okay. And ARM processor have the extra bits allocated. Okay. So the example I'm writing here. So this reserved bits, right? Okay. For this thing. So this is the example which I'm writing. For example, the J bit. So which can be found inside the flag field and is only available on the JZL state enabled processors. So which execute 8-bit instructions. Okay, done. So now time to understand the processor modes. So I said 7 different modes. Okay, so now we'll understand, look into those things. Next. Now I said 7 modes, 7 different processor modes. Again, each of these 7 different processor mode, so is either a privileged mode or a non-privileged mode. Okay, so the 7 modes which we are going to discuss now. So they some are privileged mode and some are non-privileged mode. Now, what is a privileged mode? So when I say a privileged mode, so it gives you full access for reading and writing to the CPSR. Okay, so you can read the CPSR and you can also write the CPSR. Okay, so all these bits you can read and even you can go for writing. Okay, that is what is the privileged mode. Okay, so conversely, when I say a non-privileged mode, so it allows you to only read. Okay, read access to the control field in the CPSR, but still allows you to perform the write access to the conditional flags. Okay, when you say so the processor mode is in the non-privileged mode, so then you can only read the control field. So this entire thing what I'm showing here, it can be read in the non-privileged mode. You can only read this, but you cannot modify. That means when you're operating the ARM processor or ARM microcontroller in the non-privileged mode, it is not possible for you to what? Say if this bit is 0 and if this bit is 0, you can only read them, but you cannot change them to 1. That means you cannot make your processor ignore when it is operating in the non-privileged mode. Only when it is operating in the privileged mode, you can make it to ignore the interrupts. So how? By changing, because in the privileged mode, you have access to change these 2 bits. In the non-privileged mode, you don't have the access. Okay, but even in the non-privileged mode, you have access for reading and writing the control flags, sorry, conditional flags. So these flags can be read and they can be written also, even in the non-privileged mode. Hope you understood. Hope you understood.
Yes, sir.
Okay. So if you have any doubts, please ask me. Don't hesitate. So in the privileged mode, you have full access on the entire Cpsr register. You can read anything, you can write anything. In the non-privileged mode, okay, so you have only read access to the control flags, and you can read and write the conditional flags. Okay. Now, so I said 7 processor modes are there. Out of this 7 processor modes, 6 modes are privileged modes. Okay, 6 are privileged mode. I said here the privileged mode, correct, right? So where you have full access to read and write the entire Cpsr. How many such modes? Out of the 7 modes in which the processor operates, 6 modes are privileged mode. And what are they? Abort mode, fast interrupt request mode, supervisory mode, system mode, and undefined mode. Okay, these are the 6. So you can count 1, 2, 3, 4, 5, 6. These are the 6 privileged mode. When you make your microprocessor or microcontroller operate in this 6 privileged mode, so it is possible for you to read the entire Cpsr register and write the entire Cpsr register. Okay, and there is only one. So among 7 modes, 6 are done here. 6 come under this privileged mode, and there was only one thing which is left, that is the user mode, which is a non-privileged mode. Okay, so when the microcontroller or microprocessor is operating in the user mode, it is, we say, the non-privileged mode. So you have access for reading and writing the conditional flags, but you can only read the control flags, that mode bits and thumb state bit, interrupt, fast interrupt, slow interrupt. Only those bits can be read, but you don't have the provision for modifying them. Understood, right? Hello?
Yes, sir.
Yes, sir.
Oh, you have to say confidently, yes, sir, we have understood. So if you say, so, yes, sir, I have understood. So this is not the confident way of telling that. It clearly shows that you have not understood something. So please see, you got to tell me where you're not understood. Otherwise, I'll not be knowing. So I keep explaining from my perspective, and so please, if you have anything to ask, please feel free to discuss. So I want to make you people understand it thoroughly. Okay. Please, if you have anything to ask, please ask. And if you have not understood something, please ask me. Let me clarify the things. See, when you make the microcontroller or microprocessor operate in the user mode, I say it is a non-privileged mode. So you have access, complete access to the conditional flags, that is 0 flag, negative flag, carry flag, overflow flag. You can read them and you can also write them, but you cannot write the control flags. So control flags can only be read. When the processor is operating in the 6 privileged modes like abort mode, fast interrupt request, supervisory, system, and undefined, the entire Cpsr register can be read or written. Okay, so now we'll try to understand what is an abort mode is. Okay, now the processor enters into this state. Sorry, I should not say state. The processor enters into this mode whenever there is a failed attempt to access the memory. Okay, see, normally as a user, I'll be using the microprocessor or microcontroller in the user mode, which is a non-privileged mode. Okay, now say I've written a program and I'm trying to access the memory. I'm trying to access the memory which doesn't belong to my process area, or I'm trying to access the memory which belongs to the kernel or the operating system. Then it's a failed attempt, because so the kernel will not allow me to access its own memory region. So invalid memory reference or invalid memory access or memory protection violation. Okay. ಹೆಂಗಂದ್ರೆ ನಾನು ನನ್ನ ಜಾಗದಲ್ಲಿ ಮಾತ್ರ ಇರಕ್ಕೆ ಸಾಧ್ಯ. The place which belongs to me. ಯಾರ ಪಕ್ಕದೊಂದು ಸೈಟ್ಗೆ ಹೋಗ್ಬಿಟ್ಟು ಇದು ನಂದು ಅಂತ ನಾನು ಹೋದ್ರೆ ಬಿಡ್ತಾನ? No. So then it enters into the abort mode. ಕೋರ್ಟಿಗೆ ಹೋಗ್ಬಿಡ್ತಾನ ಅವನು ಅಲ್ವಾ? So same thing here also. The processor, see, when I'm operating the processor in the user mode, and if I'm writing a program in such a way that I want to access the memory region which belongs to the kernel, so then the processor will automatically enter into the abort mode. Hope you people understood? Yes or no?
Yes, sir.
Yes, sir.
The processor will enter from the user mode to the abort mode. Okay, next, fast interrupt or interrupt request mode. So in IRQ, this is called as IRQ, interrupt request mode, and this is RQ, I guess. Let me check there, short forms. So fast interrupt request and slow interrupt request. Okay, again, so assume the processor is in the user mode and there is a slow interrupt or the fast interrupt generated by any of the external device. The processor gets into the state called as what? So if it is a slow interrupt, it gets into the state called as interrupt request state or mode. So if it is a fast interrupt, it enters into the state called as fast interrupt request mode. Okay. Then supervisory mode. So it is the mode that an operating system kernel operates in. Say for example, so I'm in the user mode. I've written my program is executing, and within my program I'm trying to call a service or a subroutine which is there inside the kernel operating system. I guess you people know what does the kernel is. Kernel is the core part of the operating system where the most basic services or facilities are residing. You know that? Hello?
Yes, sir.
Yes, sir.
Yes. Say I've written a program. Now I want my program. The program is what I have written. Okay, that is called as a user program, my program. And within my program, I need to call a service or a routine which is there inside the kernel. Okay, now when I call, what will happen? So again, the processor or the microcontroller will change its mode from user mode execution to the supervisory mode execution, because accessing to the kernel resources. So when I say kernel resources, those are the routines which are present, or the subroutines which are present, or the functions which are present inside the kernel. Now to access those things, the mode should be changed from the user mode to the supervisory mode. Correct, right? Yes or no? Hello?
Yes, sir.
See, let me go it in a simple way, because I want to make you people understand the things. See, in C programming language, to read something from the keyboard, what is the statement that you write?
Scanf.
To read something from the keyboard, what is that you write? Scanf. Scanf you write. Yes or no? You'll write the scanf statement. Is that true or not?
Yes, sir.
Yes, sir.
Okay. Now, why are you using scanf statement? Can't you write your own statement to get the data from the keyboard? So now it is not possible. It is not. See, for adding, you can write A is equal to B plus C, your return. To read something from the keyboard, it requires the kernel intervention here. So for that purpose, you're making a call to scanf. And that scanf is a library call. And that scanf again in turn makes a call to the subroutine which is there inside the kernel. And the subroutines which are there inside the kernel, they are given the function numbers. They're called as function number 1, function number 2, function number 3, something like this. Okay, it makes a call to the function number 1, that is the first function which is there inside the kernel. And that function should be executed for you to read something from the keyboard. What your scanf statement is doing is it in turn makes a call to the subroutine which is numbered as 1 inside the kernel. Your scanf is communicating with the subroutine which is there inside the kernel. Okay, now as long as the CPU was executing your program, scanf is your statement, and that scanf in turn makes a call to the subroutine number 1 which is there inside the kernel. Now when that subroutine number 1 which is there inside the kernel needs to be executed, your processor will change its state from user mode execution to the kernel mode execution. So if the processor is not able to change its state, so your kernel will not allow you to perform the execution of the function which is there inside the kernel. Understood? Yes or no?
Yes, sir.
See, if you want to enter some say restricted area, you got to take the appropriate permissions. You should go with a letter or with an ID card, something like that. Correct? Privileged access. I guess with this you people understood what is the meaning of Supervisor Remote. Yes or no?
Yes, sir.
Is it clear?
Yes, sir.
Okay. So now is the mode that an operating system kernel operates in. So whenever your program, user program makes a call to any of the subroutines which are there inside the kernel, the CPU will again change its state from the user mode to the kernel. Supervisory mode, or sometimes we also call it as kernel mode. I guess you have studied this in your computer organization. I don't know whether you have come across this or not. Sorry, kernel mode, KERNEL, kernel mode execution it's called as. Okay, next, system mode, that is another thing, is a special version of user mode, so that allows full read and write access to the Cpsr. Okay, no, I don't want to enter into the kernel mode, or I don't want to enter into the abort mode, but still I need the read and write access to the entire Cpsr, so then you can make your processor operate in the system mode. Okay, and then there is one more, undefined mode. Now the processor or the microcontroller enters into the undefined mode whenever you write some instruction, that is not there. So normally when we are writing program, so we don't remember the things and we write an illegal instruction. Okay, instruction which is not there in the ARM7 instruction set. Now when you write some instruction which is not there, now what the CPU should understand? Is it possible for it to execute it? No. Then what happens? So it enters into an undefined mode. So used when the processor encounters an instruction that is undefined or not supported by the implementation. Okay. Instead of writing add, if I write something else, okay. Now what will happen? So it enters into the state called as an undefined state or undefined mode. Now user mode is used for user program and applications. So as long as I want to write my program and perform the execution, okay, so then it is there in the user mode. So by default, we start with the user mode, and the situations will take the microcontroller or the microprocessors into the different modes. So what situation will make the microcontroller or the microprocessor to change its state from the user mode to the supervisory mode? Answer me. Answer me.
When you have to call a function kernel.
Very good. Whenever from your program, user program, you need to call the function which is there inside the kernel, then it automatically gets into the supervisory mode. Okay. When it changes its state, say we start with the user mode, and when the CPU will change its state from the user mode to the abort mode, whenever your program tries to perform an invalid memory access, or whenever it tries to violate the memory protection rule, correct? So boundaries will be there. Every process will have its own memory region. And when I say the process P1 is executing, and that process P1 is trying to access the memory which is outside its boundary and trying to access the memory which belongs to the another process P2, then that is all not possible. Okay, then again it enters into an abort state. Okay, so similarly the other states. I guess you people understood the 7 different processor modes. Yes or no?
Yes,
Yes,
sir.
sir.
Okay. Now, banked registers. Okay, so this part is clear, very clear. So this I've already shown you people. So R0 to R15, Cpsr and Spsr. So these are the 18 active registers, so which are available for use in the user mode and system mode. Correct? Correct?
Yes, sir.
Yes, sir.
Yes, sir.
Now there is something called as banked register also. So we don't call them as these things are not called as the banked registers. Okay, these are the 18 active registers which are available for use by the user and the system when the CPU or the microcontroller is operating in the user mode or the system mode. Now I said there are other modes as well: abort mode, undefined mode, supervisory mode, interrupt request mode, fast interrupt request mode. So when the CPU is in the fast interrupt request mode, okay, so these are the registers. There is something called as R8 FIQ, R9 FIQ. So I'm correct. So if I fast interrupt request, so these are the banked registers. How many banked registers are there? Totally 20 banked registers. So when your microcontroller or microprocessor is operating in the fast interrupt request mode, so these are the registers. So R8, R9, okay, FIQ. It will not make use of these things. So these are for the user, and these are when the CPU is operating in the fast interrupt request mode. So you can count them. There are 20 banked registers. 1, 2, 3, 4, 5, 6, 7, 8. And these are the registers which are used when it is operating in the slow interrupt request mode. How many are there? 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 20 banked registers are there. So why they are called as banked register? Because these registers are not visible to the users, and user visible registers are these registers. Hope you understood. Yes or no?
Yes,
Yes,
sir.
sir.
And easy to remember also. These registers R8 FIQ, and they are labeled like that. R13 IRQ, okay, slow interrupt request, and then R13 SVC. Okay, this is a different register and this is a different register. So supervisory mode, okay, SVC, and then undefined mode, and then abort mode. Okay, next. Okay, there are 37 registers in the register file, strictly speaking. So we don't take this into account till Bardila. I told 18 active registers. So in these 18 active registers, okay. So this we don't take this into account because majority of the time we don't use this and we don't modify this. Okay, so we use this Cpsr. So 17 from here and 20 from here. So it has 37 registers. Okay. There are 37 registers in the register file, and among these 37, 20 registers are hidden registers, or also you can call them as banked registers. Why they are hidden? Because they're not visible to the user. Even now, in the previous class, we executed 1 or 2 sample programs, and what were the registers you're able to see there? R0 to R15, Cpsr and Spsr. Apart from this, so none of the other registers were visible to you. So that are the banked registers, which will be used by the microcontroller. So when the situation demands for the microcontroller to enter into the various other modes. Hope people understood?
Yes, sir.
Okay. So they are available only when the processor is in a particular mode. Okay, and they're not visible for us. Okay, now see, this is the mode. How many bits are reserved? 5 bits. Let me go back. Here, 5 bits. Bit number 0 to bit number 4. Okay, now when the microcontroller is operating in the user mode, okay, so and is it a privileged mode? No. So this is the value. 4th bit is 1, 3rd bit is 0. If this is the value, okay, here in the Cpsr register, if the 4th bit is 1 and the remaining 4 bits are 0, 0, 0, so your microcontroller is operating in the user mode. And similarly, so whenever say you are written some instruction which is not identified by the ARM controller, so then it enters into the undefined state by changing the mode bits to something like this. And then the system, if you make all of them as 111, it is the system mode, supervisory mode, and then interrupt request, fast interrupt request, abort. So like this, you can have 32 different modes, but as of now, there are only 7 modes supported. Did you understand? So among the 7 modes, so this is the only non-privileged mode, and these are all the privileged mode. Okay, and their abbreviations: abort, ABT, FIQ, IRQ, SVC, SYS, undefined UND, and user mode is USR. Is it clear?
Yes, sir.
Now, after understanding the processor modes, so next thing to understand is the processor state. Okay, so as already you know, so 3 states are possible. So don't confuse with the states and the modes. So ARM state, thumb state, and Zessel state. So when the processor is operating in the ARM state, so default state is this. So your T bit, that is the 6th bit, and the 24th bit, if both are 0, 0, then your processor is operating in the ARM state and it uses a 32-bit instruction. Similarly, the thumb state, okay, when T bit is 1 and J bit is 0, that is the 6th bit is 1 in Cpsr and the 24th bit is 0, so then your microcontroller is operating in the thumb state and it uses 16-bit instructions. Okay. Next. Zazzle state. So when T bit is 0, J bit is 1, okay, so it is in the Zazzle state and it uses 8-bit instructions. And especially this Zazzle state is used to execute the Java bytecodes. So I said you write the programs, embedded C programs, correct, right? So now if you enable this, if you make your microcontroller operate in the Zazzle state, so you can go for writing the Java codes also, Java programs you can write. Okay, so to execute the Java bytecode, the Zazzle technology plus a Java virtual machine is required. So you should have JVM installed on your embedded device, and if your microcontroller is enabled to operate in the Zazzle state, even your Java program works here. So it's not like you should write the embedded C program. So understood?
Yes, sir.
Yeah. Next, this is the comparison of ARM and thumb state, because we don't focus much on the Zazzle state. So our focus will be only on the ARM and the thumb state, and that too, again, thumb state also we don't discuss it in deep. So our focus will be completely on the ARM state. Okay. So ARM state, so T bit should be 0. So thumb state, T bit should be 1. And instruction size here is 32-bit, as you all of you know. When the controller is operating in the thumb state, instruction size is 16-bit. And then the number of instructions when it is operating in the ARM state, 58 instructions. So it is 30 instruction here. And conditional execution. So majority of the instruction conditional execution is possible. That means it is possible for you to embed the conditions as a part of the instruction. But when it is operating in the thumb state, so it is not possible for you to embed the condition for all the instruction, because in the earlier classes I showed you, you can embed condition for the move instruction. So but here, when the microcontroller is operating in the thumb state, so it has its own limitation. So you can have conditional execution only for the branch instructions. And then data processing instruction, they have access to the barrel shifter. I said one of the ALU input is connected with the barrel shifter. So now here, so separate barrel shifter and ALU instruction. So they are completely separate. Okay. So and then program status register. So can be both read and written in the privileged mode. So we understood 6 privileged mode. So to list what are the 6 privileged mode. Let me check whether you have understood all the 6 privileged modes or not. What are the 6 privileged modes? Can you make a list of them? Abort, good.
Fast interrupt.
Undefined.
Fast interrupt.
Interrupt.
Slow
Undefined.
interrupt.
Undefined.
Undefined. Okay. 4 finished.
Supervisor.
Supervisory. Good. 5 finished.
System.
These are the 6 privileged modes. Okay. And then so here when it is operating, there is no direct access. Okay. There is something called as privileged mode, which has direct access for reading and writing to the Cpsr. And now the register. So when it is operating in the ARM state, 32-bit state, so you have access to all the 15 general purpose register plus the program counter. But here, so 8 general purpose register plus 7 I registers. Even I don't know what are those 7 I registers, because our focus will not be on this. Our focus will be only on the ARM plus PC. Okay. So he says, as far as I know, I think it is the same general purpose registers. Again, I think there are limitations. Okay, so that means it will allow you to use from R0 to R7, and after R8 to R15, I guess there are restrictions. So this R8 to R15 are called as IR register. Okay, but this R8 to R15 in thumb state, I think you cannot freely use them. Okay, as you use R0 to R7. So there is restrictions again in this. So hence is separated then. Okay, so this is what the comparison. Now the Zazzle state instruction features. So this is well known. To make it to operate in the Zazzle state, T bit you have to make it as 0 and J bit you have to make it as 1, and size of the instruction is 8-bit, and the core instruction. Okay. So it is possible for you to even run the Java codes also if you enable this Zazzle state. Next. Yeah, interrupt masks. Knowing more about the interrupt masks. So as already mentioned, interrupt masks are used to ignore they make the processor ignore the instructions or stop the interrupt request from interrupting the processor. That is what is masking. So there are 2 interrupt request levels. One is IRQ, slow interrupt request, and FIQ, that is fast interrupt request. So bit number 6 is reserved for FIQ, and bit number 7 is reserved for IRQ. that slow interrupt request that you have already seen. And this is the more detailed view of the Cpsr, which we understood already. Okay, so these are the mode bits from here to here, M0 to M4, and this is the state bit, thumb state bit, and this is fast interrupt bit, and this is slow interrupt bit. So if you want to mask the fast interrupt, make 6th bit as 1. See, I bit masks IRQ when set to binary 1. So if I make this bit as 1, so the slow interrupts are masked, are disabled, are prevented from being delivered to the processor. So if I make this bit as 1, so the fast interrupts are prevented from being delivered to the processor. And okay, all this is, these are the reserved ones, and in this again we understood the 24th bit as the J bit, Jazzle state bit, and this is overflow, carry, 0, and negative. Okay, just the complete the more details, same thing what we understood earlier. So but our focus in this slide was on the interrupt mask, that is I and F, which I had explained earlier. So conditional flags, this also I've explained. Okay, these are the conditional flags, and there is one more here. So this 27th is Q flag. So again, we don't use that. So that is saturation flag. So we don't use that. Let us not worry about it. Next is overflow flag, carry flag, 0 flag, and negative flag. And you can see here. So what is overflow flag? Result causes the sign overflow, and then carry, the result causes an unsigned carry, and then 0, the result is 0. That is if the result of the most previous recent operation performed by the ALU is 0, then this flag is set. If the most recent operation that is performed by the ALU result in a carry, this is set. If the most recent operation that is performed by the ALU resulted in an overflow, then this flag is set. And if the most recent operation that is performed by the ALU resulted in a negative result, so then you have this flag set. Okay, or I also mentioned this, always the most significant bit, the 31st bit is the sign bit. I have an example here, say sub S. So there is a suffix S. Sub is subtract instruction. So if there is a suffix S added, so it is going to affect these flags. Okay, so if the result of the subtract operation gives you the 0 result, so then the 0 flag is set. Now I don't want this flag registers to be affected. So let me do the subtract operation without affecting the flag registers. So then you don't have to use this sub S. S suffix is not required. You just write the instruction as sub and go for specifying the operands. So it subtracts and it will not go to go for affecting the 0 flag. If you want the 0 flag to be affected, so then you got to use sub S. Hope you people understood.
Yes, sir.
Okay. See, subtract R1, R2, R3. So can subtract the content of register R3 from R2 and store the result in R1. If the result in R1 is not 0, what instruction I used? Sub. Okay. So whether it is 0 or not 0, you don't have the carry 0 flag affected. So if I want the 0 flag to be affected, then instead of sub, I need to make use of sub S. I need to use the sub instruction with the suffix S. Sub S, R0, R1, R2. What it will do, it will try to subtract the content of register R2 from R1, and if the result is 0, if the content of register destination register R0 is 0, then the 0 flag will be set. So if the result is not 0, then 0 flag is not set. Clear, right?
Yes, sir.
Okay.
Yes, sir.
Now, so here in our book, the prescribed textbook, so we use a notation. Okay, so this is what is your Cpsr. Now, what is the kind of notation we use in order to remember all these things? See here, SVC. Okay, this is supervisory mode. So this bit configuration says it is in this supervisory mode, and so this T. See the case of this letter. It is in lowercase letter. So if I'm writing it in lowercase letter, the corresponding bit value is what? 0. And to say this bit, sixth bit is 1. So what is the case of this letter F? Uppercase. So OP people are able to see this? Hello?
Yes, sir.
Okay. So this is how I write it. So this is the convention what we use. See, this is 0. Negative flag it is. I'm writing it in lowercase. And this is again 0. 0 flag. I'm writing it in lowercase. And the carry flag is 1. I'm writing it in uppercase. Okay. And overflow flag is 0. And Q, saturation flag, is also 0 in lowercase. And Zazzle state is 0. So this is how I write it. Now, just by looking into this, you can see which are the flags that are set and what is the mode. Okay. Now, by looking into this, you can see. So Cpsr henceforth, instead of writing it in terms of zeros and ones, we write it like this. So N, Z, and C carry flag is set, and then here the fast interrupt is set, and the rest all are zeros, and this is in the mode supervisory. Hope you understood. Hello.
Yes,
Yeah, this is the notation. This is the notation which we follow. Okay. So henceforth, if it has written something like this, you got to see which is in the uppercase letter, and that particular flag is set, and the rest all is not set. Okay. Here in this case, we have carry flag and the fast interrupt flag set, and the rest all are zeros. And this is saying it is the supervisory mode. For abort mode, instead of SVC, you get it as ABT. ABT. And for user mode, USR. Okay, something like that. These abbreviations we make use here. I'll show you the abbreviations. These abbreviations written in uppercase. That's all. So till here it is clear, I guess. Understood now?
yes, sir.
Okay. Now conditional execution. So it is possible for you to embed conditions within the instruction. Okay. So most instructions have condition attribute that determines if the microcontroller will execute it or not based on the settings of the conditional flag. Say for example, I want the move instruction to be executed only if the condition is satisfied. Okay. So move, there is something, let me show you here. These are all the conditional mnemonics. Say, let me write, take a pen. Say move. If I write something like this, R0, R1, what will happen? So this will always move. It will take the content of register R1 and it will always move to register R0. Now I want this statement to be executed only if the result of the previous operation that is performed by the ALU is 0. Then what I do? Move. Now to this move instruction, I can embed the condition EQ. EQ. So this is the condition which I'm embedding. R0, R1. Now, this statement gets executed only if the result of the previous operation that is performed by the ALU resulted in the 0 flag to be set to 1. If 0 flag is 1, what does it mean? The result of the previous operation performed by the ALU is what? 0. So then you move it. If the result of the previous operation performed by the ALU is 0 and the 0 flag is set, move the content of register R1 to R0. Otherwise, don't move. OP people understood this?
Yes, sir.
Yeah. See, difference between this and this. This is also move, but without the condition embedded. So this is also move instruction, but with the condition embedded. Now what this says, always move the content of register R1 to R0. But what this says is move the content of register R1 to R0 only if the 0 flag is what? 0 flag is? 0 flag is?
1.
1.
1. If 0 flag is 1, what does it mean? What is the meaning of 0 flag is 1?
The latest execution resulting
Yeah.
0.
The result of the most recent instruction executed by the ALU is what? 0. Understood, right?
Yes, sir.
Is it clear?
Yes, sir.
Yeah, that's. And similarly, this is one such condition mnemonic that can be embedded into an instruction. So, but there are many such. So not equal to. So if I want to move the content of register R1 to R0, only if the result of the previous instruction executed by the ALU is not 0, so then what is that I have to do? NE. What this NE will check? NE will check for the 0 flag to what? 0. It checks Z I have written in lowercase here. So what it will do? NE will check if the 0 flag is 0, then it will move the content of R1 to R0. Get it? And similarly, other things are there. And all these things you'll understand as and when we go there. It is not necessary for you to remember right now all these things. So gradually, as and when we go, proceed with the later topics, you will get to know all these things. Okay. Shall we move on to the next one?
Yes, sir.
Okay. Now pipelining. So I think I don't have to spend much time on this because in my earlier classes I've explained clearly on the pipelining concepts, and ARM7, as you know already, it is a 3-stage pipeline processor. So it has a fetch unit, decode unit, and execution unit. Okay, and what fetch does, decode does, execute does, you know. And this is one example how the instructions get executed in a 3-stage pipeline processor. So first clock cycle, you have the first instruction fetched. Okay, in the second clock cycle, there are 2 things happening. So add instruction is getting decoded and subtract instruction is fetched. In the third clock cycle, there are 3 things happening. Add is getting executed, subtract is getting decoded, and fetch is compare instruction. CMP is compare. Compare instruction is fetched. So all the 3 things are simultaneously getting executed. So now, okay, this is what is ARM7, 3-stage pipeline processor. What about ARM9? It's a 5-stage pipeline processor. So it has a fetch stage, decode stage, execute stage, memory, and then write back. So total 5-stage pipeline processor it is. Now ARM10, if you take, it's a 6-stage pipeline processor. So fetch, instruction issue, decode, execute, memory, write. So it's not necessary for us to understand what is the functionality of each of these stages, because our focus is completely on ARM7. So this is just for your knowledge. Okay. So it's a 5-stage pipeline processor. ARM9 is a 5-stage pipeline processor, whereas ARM10 is a 6-stage pipeline processor. Okay. And say since we have the number of stages increased here, so it's just a comparison here. So ARM9, okay, throughput is around 13% more than compared to ARM7. So what is throughput is? How do you define the term throughput? You know, what is throughput? Hello?
Don't know, sir.
Don't know. So throughput is amount of work done per unit time. Or amount of work done per second. How much amount of work you're able to do in a second. Okay. So now, if you take ARM9 processor, ARM9 can do 13% more work than compared to what ARM7 processor in a second. Why? Because it has more number of pipeline stages. Now here in a ARM7, the maximum overlapping that you can do is only what? 3. In third clock cycle, there are only 3 things overlapped. And on ARM9, which is a 5-stage pipeline processor, in 5th clock cycle, how many things will be overlapped? 5 things. And here in ARM10, how many things you overlap? In the 6th clock cycle, 6 things. Okay, so 6 different things are overlapped, and all of them are getting executed simultaneously. In that reason, so the amount of work done by ARM processor is 13% more than the ARM7 processor per unit time. So if I'm taking the amount of work done by ARM processor in 1 second, and if I'm comparing the amount of work done by the ARM 9 processor in 1 second, so the amount of work done by ARM 9 is 13% more than ARM 7. So now time to compare the amount of work done by ARM 10 processor with the amount of work done by ARM 7 processor in a second. Okay, so now it is 34% more. So the ARM 10 processor does 30% more, 34% more work per second than compared to the ARM 7. So OP people are able to understand.
Yes, sir.
Okay. Okay, what we'll do is let me stop. I got my mouth dried. Okay, so we'll stop here. Okay, and from here we'll continue in the next class. And again, all these things are very interesting. So you'll get you need to understand a lot of things.
Sir,
Okay.
excuse me, sir.
Yes, ma'am.
Sir, ARM uses how many buses? Like it uses multiple bus or single?
See, ARM, we don't have external bugs. There is no something called as PCI slots here. All are internal buses. Okay. Because all these components, interrupt controller, memory controller, CPU, everything is there on the same chip. No, I
Okay,
don't know.
sir.
Say when I go back to the college, okay, because now it is work from home for us, okay. So probably I think May 10th onwards, if I get back to the college, I'll take the photo of these ARM controller chip and I'll send you. So everything is there on the same chip. Okay, I'll just show you. When you look into that photo, you'll understand. So all are internal buses. Okay, and you cannot see them.
Okay, so but they use multiple, no, sir, like more than one bus.
More than one bus for what purpose? In what context you're asking? That I'm not able to get.
Sir, actually, can you go back to that slide where you showed the pipelining process, like three clock cycles?
This one? No?
Yes, sir. Actually,
No,
fetch,
this one.
decode,
This
and
one, I
execute.
guess. Yeah, this one, I
Yes, sir.
guess. Yeah, yeah,
Fetch, decode, and execute, sir.
yeah.
Actually, if it uses multiple buses, it can be done in minimum of 2 clock cycles, right? No, sir. Like if you
Yeah,
use
yeah.
a single bus,
I got your point. See,
so why you use 3 cycles? And also even this thing changes when I forgot the terms. I'm not very well acquainted with the terms. Like the comparison, it decreases or something like that.
yeah, I got your point. See, again, the pipeline what I've shown is at the very high level. See, in the 7th semester advanced computer architecture, you'll look into the detailed design of pipelining. So all those things, if I start explaining here, it'll take more time. See, so again, there are a lot of difficulties here as well. See, as you said, it is with respect to the clock cycles again. See, when I'm applying the clock cycle, so this is normally we write the clock cycle something like this. Hope people are able to follow. This is a clock cycle. And this is a clock cycle. This is a clock. See, when I apply the clock cycle, I have to apply the clock cycle simultaneously across all the stages. Hello.
Yes, sir. Yes, sir.
It is not like multiple paths. It is only a single path. So from here to here, you have a single path. Here to here, single path. Now, see, here in the previous, so just go back to the second clock cycle. Add instruction was here. Subtract instruction is here. In the third clock cycle, the new instruction compare should get into this. And by the time compare gets into this, the subtract should shift into this. Correct, right? And these things should happen simultaneously. Hope people are able to understand.
Oh, got it, sir. Got it.
See,
I got it. I got it.
For compare to appear here, the sub should make a room for it. Otherwise, what will happen? See, if you're not applying the clock cycle simultaneously across all the stages, so then the compare instruction will come and interfere with what? Subtract. Or the subtract instruction which was in the fetch stage will go and interfere with what? The decode stage. Hope you people are following?
Yes, sir. Got it. Got it.
See, it is not serially applying the clock cycles. You got to parallelly apply the clock cycle across all the stages. And again, there is a problem. Say, for example, so the complexity of the circuitry also plays a major role here. So when you're designing these stages, they should be designed in such a way that, okay, so all of them take the same number of clock cycle to complete their task. Say, so this is a clock cycle. Let me write it very clearly. And one more clock cycle here, and one more clock cycle here. So this clock cycle is for this, and this clock cycle for this stage, and this clock cycle for this stage. Assume I'm applying the clock cycle simultaneously across all the stages. In third clock cycle, these are the clock cycles applied simultaneously. So now here in the even in the clock cycle, there is something called as this is beginning of the clock cycle. OP people all know this. This edge, what you're seeing here, the rising edge of the clock cycle. Yes or no?
Yes, sir.
This is rising edge of the clock cycle, and this is the falling edge of the clock cycle. This is again rising, falling, rising, falling. Now, see, this is execute, this is decode, this is fetch. So the complexity of the circuitry is not uniform. So now when I say execute, it is the complexity of the circuitry is more, and this is slightly less, and this is I can say very less. Okay, so since the complexity of this fetch stage circuitry is very less, so it may finish shifting this compare instruction. Sorry, let us speak with respect to this. So since the complexity is very less for the fetch stage than compared to the decode and execute, so the moment this fetch stage ceases this rising at the clock cycle, it will push this sub instruction to the next. Hope people are following. It will not wait until it sees the falling edge. The moment it sees the rising edge of the clock cycle, it is able to push. Got the point? Hello?
Yes, sir. Yes, sir.
Yeah. Now take this. So the complexity of this decode is slightly, assume this is slightly higher than this, okay? Higher than the fetch stage. Now this requires a finite amount of time. Say the rising edge of the class, so it cannot push this instruction to the next, okay? So it takes some time. Say it is doing at the middle of the clock cycle. So what this is doing, the moment the fetch stage, the moment it sees the rising edge of the clock cycle, it is pushing the sub instruction to the next stage. So but this, since the complexity of this circuitry is more, so say it is finishing its task at the middle of the clock cycle whenever it sees the middle. That means for this time, for this duration, so this subtract instruction will come and collide with the add. Yes or no?
Yes, sir.
It comes and collides with add. And again, so what we do, so we add something called as pipeline latches here. So all those things are not here as a part of your syllabus and discussion. All these things you'll understand when we go to the 7th semester. And even I love that subject a lot. Advanced computer architecture. We add something called as pipeline latches. So why these pipeline latches are added? Just to solve this problem. Just solve this interference problem. So when I apply the clock cycles, instead of letting the instruction from here directly flow into the other, we make it to go and install in this latch. Understood? So this may be doing at the rising edge of the when it sees the rising edge of the clock cycle, it will push here. And again, this might do it when it sees the middle of the clock cycle, it will push here. Okay, and this might do when it is seeing the falling edge of the clock cycle, but the complexity of the execute stage will be always higher than compared to the decode and fetch. So say it is completing its process when it sees the falling edge of the clock cycle. So now there is no interference. These latches are used just to avoid the interference. So we don't have something called as multiple paths or the multiple buses here. So it is the sequential flow. The instruction should flow one after the other. Hope you understood.
Yes, sir. I got it.
Yeah. So there are a lot of things even in the pipeline. That pipeline diagram itself is a very big diagram. Okay, so that so if I'm there for as a teacher for you people for handling the advanced computer architecture in 7th semester, so I'll be very fortunate because I'm teaching you people this, and so you'll all get an opportunity to understand how the pipelining operates, and I love that subject a lot. Okay.
Thank you, sir.
Yeah. So we'll stop here. Let me download the attendance, and in the next class we'll continue from here. Okay, so pipeline executing characteristics. So, but if people are joining late to the class, so try to join quickly. Okay, and I've recorded this session also because I got a few requests from the students asking for the recorded videos. I've recorded. Today only I recorded. First 1.5 module recorded videos was not there in my Google site because all those things in the previous year it was covered through offline mode. After that, there was a lockdown and everything went through online. For that, I have the recorded videos, but for this 1.5 module, so let me make it. So today only I've recorded, and previous to this, I need to make myself the recorded videos and share with you people. Let me do that.